Okay. Good afternoon, everyone. This is Wang from Beijing Jiaotong University. It's only here to introduce our work, Fuzzing CPP compilers via type-driven mutation. First, let me introduce some background. So as we all know, CPP was a very long history programming language. It was created in 1985 by Benjamin Strostrup. It features high performance and direct memory access, making it an important system-level programming language. Many essential fundamental software are written in CPP. For example, the C and CPP compiler themselves, and Clang and GCC, and important GVM, OpenGDK, and some important databases like MySQL and Redis, and Chrome browser, and also Z3 solver and CUDA, TensorFlow, and Microsoft Windows kernel. So all these important products are written in CPP. CPP is a compiler language. It's relying on compilers to translate source code into target code. So a compiler is essential in the ecosystem of CPP. However, as many complex software, compiler also may have bugs, and these bugs may cause crashes during compilation. And the worst thing is, it may incorrectly transform the codes. It may transform the correct source code into incorrect executables. So these defects in compilers may propagate to all the generated programs. Therefore, testing CPP compilers is crucial. As we all know, CPP has a very complex type system. Anyone who have learned CPP knows the struggle. The learning curve is steep and long. So there is a joke in Chinese society, as if one developer who's writing his programs in CPP, and if he have learned 3 years, he told to other one that he mastered the language. But if he have 5 years experience, he said he understands the language. And if he had 10 years language, he say he just heard about it. So there are also many funny pages, funny figures in the internet. Compared with GVM languages like Java, CPP features have much more complex type system. It is a static typing, but also with runtime mechanisms, and it also supports type inference. It has the keyword auto, and the implementation of generic programming in CPP is based on template, not type arrays such as Java. It also supports type alias. Only a few programming languages support this feature. And it also supports complex inheritance hierarchies. For example, it supports multi-inheritance. Therefore, CPP's complex type system poses high significant challenges to compiler correctness. Let's see a motivating example. This is a bug, a GCC bug, had been hidden for 19 years before we reported it. So this program first defines a struct, a class, and it has one constructor taking one integer as input, and the third line is overloading casting operator. So in the sixth line, it has a ternary expression which requires the x and the zero, the integer 0, they should have the same type. However, x is a constant reference of a. And the 0, if we don't have the explicit, it will go through the line 2 to call the constructor and return an object of A. But if we insert an explicit here, if we don't have the line 3, the word this program should be invalid. However, since we have line 3, so the 0, which is the non-pointer in C program in C type system, and would change would be casted into a type A. So this one still be valid. However, the compiler incorrectly rejected this program. Currently, there are two main categories of compiler fuzzing approaches. One is generation-based, such as C. Smith and Yapgen. The one is mutation-based, such as EMI, which is proposed by Zheng Su, and Gracie and Metamute. However, both categories struggle to fuzzing type-related features. Generation-based methods struggle to produce programs that fully access the complexity of type systems. And mutation-based approaches, and currently they overlook the type system-aware mutation operators. Therefore, we propose TY-mute. So here's the overview of TY-mute. Given a valid program, a CPP program, we first perform some necessary analysis to extract some necessary data structure, and we perform the mutation by our type-driven mutation operator. And if the operator is a well-formed mutation operator, the valid program should keep it validity, and the output also a valid one. So the compiler cannot reject it. If the program is generated by a not well-formed mutation operator, the correctness is unknown. So we further check it with well-formed rules. If the rule rejects the program should be invalid and cannot be accepted by the compiler. Otherwise, we don't have enough test oracle, so we employ differential testing. We model the CPP into a DSL, and we also build some. We also extract some necessary data structure, such as inheritance graph, accessibility, and we also model the type system. We support nominal type, which support inheritance, and we also support structural type. And based on this, we build a type lattice of the program. Based on this type structure, we design and implemented 30 mutation operators across 5 categories. And the categories are focusing about inheritance, template, type convention, and accessibility, and also object lifecycle related. Here's some operator examples. One is generic narrowing. It will change one structural type to its subtype. Here, and the second one is order lifting. We will lift one expression to its lambda. And we also construct some multi-inheritance structure. So traditional compiler testing compares compilation results across different compilers to detect inconsistencies. So this requires all input programs to be valid. However, when testing type system, we need both valid and invalid input programs. So valid for check correctness, while invalid one check error handling. So therefore, the test oracle become more challenging. So we handle this by mutator classification and the human writing checking rules. So given a valid program, if it is generated by a well-formed operator, it should be valid. And if it's produced by a not well-formed operator, we further check it by rules. So here's the evaluation. During the bug hunting experiment, we totally reported 102 bugs to GCC and LLVM, and 56 of them have been confirmed as new bugs. And here are the symptoms. As we can see, more than 40% fall into the accept invalid and reject invalid, and they cause miscompilation. Among the 56 confirmed bugs, seven of them have remained hidden for over 20 years, and 22 for 10 years, and 39 for 5 years. And one long-lasting issue has confirmed to be the root cause of a real-world issue in TensorFlow. And one unconfirmed bug led the compiler developer to submit a new issue to the CPP language standard. So here are some bug examples. This one is the root cause of TensorFlow. And here are some issues. Here are some bug examples. And also, it received some interesting comments by developers. The most interesting one is the GCC, the LLVM. The developer referred to Git pull request 30 years ago, and he commented, "Wow, looks like I got this wrong 30 years ago, oops." And we also received some comments from the developers. Okay, thank you.
Thank you. We have time for around 2-3 questions. If there's no question yet, I would like to ask, what was the bug that led them to fix the standard, something in the standard? I think you scroll very quick. Maybe just leave the laptop for a second, or if you can describe it.
Sorry, beg your pardon?
What was the bug that led to the change of the C++ standard? And to add it, so they fixed something in the standard? One of the bugs that you found?
It's about, we import a global declared enum into inside the class. So the behavior is unspecified by the standard.
So they have to either say it's unspecified or to create a subsection describing what's the case, what they did in the end, or just to mention that is, because I know if it's unspecified, it's also saying it's unspecified. So was it a case that it was not mentioned that this behavior is unspecified behavior, or was it a case when they added this behavior to the standard?
And the developer just commented that the behavior is totally unmentioned by the standard. So.
Okay. Yeah.
Okay.
Yes, I think.
I have a quick question about the soundness issue where the compiler accepts invalid programs. So to identify, I remember the 13 unique bugs. Did you have to manually inspect the type error emitted by the compiler to come up with the unique test cases, or did you have any kind of automated process to classify those into some equivalence classes of type errors?
All the output results, for example, the results of different testing or rejected by the rules, we would check them manually.
Oh, okay, thank you.
Thank you.
Yeah, I think there was another person but maybe we take it over the coffee break. Thank you for the talk.